Welcome to the Explainer. I am so thrilled to have you here today. So, have you ever actually stopped to think about how the universe, literally everything around us, including you and me, has this built in physical stubbornness to it? Well, it does. Today, we're taking a really fun deep dive into the fascinating rules that govern how things move, or in a lot of cases, why they absolutely refuse to move. We're going to transform some incredibly foundational physics into a clear, visual journey to understand exactly how forces affect motion. Here's a quick roadmap for today's explainer. We're going to kick things off with the magic of motion, then look at balanced versus unbalanced forces, dive into this idea of the stubbornness of objects, meet some pioneers of physics, and finally, look at how to graph zero net force. All right, let's jump right in. Okay, let's dive into Section 1, the magic of motion, and how physics shows up in our everyday lives. So I want you to picture something. Imagine a beautifully set dining table. Now imagine grabbing the edge of that tablecloth and giving it a sharp, super fast yank. What actually happens when you pull a tablecloth out from under a plate? Does the plate go crashing to the floor, or does it stay right where it is? Just kind of hold on to your intuition here for a second before we reveal the science behind it. Because take a look at this. We've got two scenarios here that look totally different, but they're actually driven by the exact same invisible rules. On the left, there's that classic magic tablecloth trick, where pulling the cloth quickly leaves the dishes completely undisturbed. But on the right, you've got a pro cricket fielder deliberately moving their hands backward to catch a wildly fast ball. One is all about keeping an object perfectly still, and the other is about safely stopping an object moving at really high speeds. But both are an absolute masterclass in understanding how motion behaves. And you know, that really hits the nail on the head for what we're talking about today. The laws of motion basically explain how forces affect the motion of objects. So whether it's a heavy apple suddenly snapping off a branch and falling to the earth, or skateboarders sliding smoothly down a concrete ramp, there are these invisible pushes and pulls, forces, constantly at play. And these forces are actively determining the final outcome of every single movement in our physical world. Which brings us nicely to Section 2, balanced versus unbalanced forces. Let's peel back the layers a bit and look at the actual mechanics that cause an object's state to change. Let's break down the chain reaction of motion here. Force is kind of like the initial trigger. When a force is applied, it causes acceleration. And what does that acceleration do? Well, it creates a change in velocity. As you can see in those handwritten notes right there, a change in velocity means an object is either speeding up, slowing down, or changing its direction. If none of those three things are happening, then velocity is not changing. It's a pretty perfect cause and effect loop. But here is the absolutely crucial distinction. On the left side, we've got a balanced force. This is what happens when all the pushes and pulls on an object completely cancel each other out, meaning the net force is exactly zero. When that happens, acceleration is zero, and the object just keeps doing whatever it was already doing. Resting stays resting, moving stays moving. But then look at the right side, unbalanced force. In this case, the net force is not zero. Say you have 10 newtons pulling one way and 7 pulling the other. You're left with a net force of 3 newtons. Whenever forces are unbalanced like this, the object's state is absolutely guaranteed to change. Now, what's really interesting about this next part as we move into Section 3 is how we actually understand this stubbornness of objects, also known as inertia. Let's loop back to our tablecloth and cricket examples for a second. Notice how the concept of inertia is directly linked to the word stubborn, or in Hindi, hathi and zidi. I absolutely love thinking about it this way. Objects are literally just stubborn. They have this inherent physical nature that aggressively resists changing whatever it is they're currently doing. Let's really cement that definition. Inertia is formally defined as the tendency of objects to resist change in their state of rest or uniform motion. Make sense? So when the magician yanks that tablecloth, the plate doesn't fall because of the inertia of rest. It is stubbornly committed to staying still, and the force of the cloth is just way too quick to drag it along. On the flip side, that incredibly fast cricket ball has tremendous inertia of motion. It stubbornly wants to keep flying forward, which is exactly why the fielder has to pull their hands back to gradually absorb that force without getting injured. All right, moving on to Section 4, pioneers of physics. Let's talk about the historical breakthroughs that actually got us here. Because, getting to our modern understanding really wasn't easy. Back in ancient times, people completely misunderstood motion. They figured you needed a constant, continuous force just to keep an object moving at a constant speed. Basically, if you stopped pushing, they thought the object's natural state was to just stop. It wasn't until the 17th century that Galileo totally flipped the script with his thought experiments, which eventually paved the way for Isaac Newton to publish his definitive laws of motion in 1687. Let's take a closer look at the guy who really kicked off this massive shift, Galileo Galilei. Living from 1564 to 1642, Galileo wasn't one to just accept the ancient dogma. He actually challenged it using pure logic and these brilliantly simple thought experiments about objects moving along horizontal planes. He argued something that was super counterintuitive for his time. He said, if a body moves along a horizontal plane and all impediments to its motion are removed, it will continue to move indefinitely. I mean, wow. This was a massive aha moment in the history of science. He realized that things don't naturally want to stop. They only stop because hidden impediments, things like friction or air resistance, force them to. Without those, an object's stubbornness would just keep it moving forever. And then enters Sir Isaac Newton. Newton took Galileo's amazing concept of this stubborn tendency, officially gave it the name inertia, and used it as the foundation for his monumental first law of motion. Writing his 3 laws in 1687 was arguably the defining moment in the history of physics. I mean, the guy's contribution was so immense that we literally named the standard unit of force after him. Oh, and just a quick pro tip on that. When you're writing out the unit of force, remember it's a lowercase n for Newton, but the symbol itself is a capital N. Let's move to section 5 and see how this all builds into translating these ideas into actual data by graphing zero net force. Let's look at a scenario where absolutely zero net force is acting on an object. Based on everything we just covered about balanced forces and inertia, if there's no net force, there are really only 2 possible realities for that object. Step 1, the object is completely at rest, or step 2, the object is moving with a constant velocity. Let's see what those 2 situations actually look like on a graph. These diagrams brilliantly illustrate the math behind the stubbornness. Look at the 2 graphs on the left, representing an object at rest. On the position time graph, time is marching forward, but the object's position is a totally flat line. It is not going anywhere. Right below that, its velocity time graph is a flat line sitting exactly at 0. Now compare that to the 2 graphs on the right, where an object is moving with constant velocity. The position time graph shows this steadily climbing straight diagonal line because its position is changing at a uniform rate. But crucially, look at its velocity time graph. It's a perfectly flat horizontal line above 0. It's got speed, but that speed is stubbornly refusing to change because there is no unbalanced force acting on it. Pretty cool, right? And that actually brings us to the end of our journey today. From the magic of a tablecloth trick to the genius of Galileo and Newton, all the way down to the solid logic of a velocity time graph. We've seen how the rules of motion pretty much govern everything around us. So I want to leave you with this final provocative thought. If the universe is naturally stubborn and objects only change what they are doing when forced to, what invisible forces are secretly acting on you right now to change your state? Think about it. Thank you so much for learning with this explainer today. Keep your eyes open and try looking for the stubbornness of motion in your everyday life.